Welcome. Today, we're exploring how pressure differentials can help prevent cross-contamination. Dr. S.K. Singh will guide us through the science and practical uses of this approach. It's a powerful tool for keeping environments safe and clean, and we'll see how it works step by step. Let's get started. Let's talk about cross-contamination, what it is, and why it matters. Cross-contamination happens when unwanted substances move from one product, process, or area to another. This can lead to serious consequences like product recalls, batch rejections, or even risks to patient safety. It can come from airborne particles, microorganisms, dust from active ingredients, or simply from people and materials moving around. For example, dust from tablet compression might drift into a nearby packaging room if pressure controls aren't right. Understanding this helps us prevent these risks. Let's talk about pressure differentials and why they're crucial in contamination control. Air naturally moves from areas of higher pressure to lower pressure. We use this principle to control airflow, keeping contaminants out of critical manufacturing spaces. The benefits are clear: protecting the product, separating environments, controlling microbes, and cutting down airborne contamination. For example, in a sterile filling suite, maintaining higher pressure pushes clean air outward, stopping dirty corridor air from sneaking in. It's a simple idea with a powerful impact. When it comes to regulatory expectations, there are some key requirements we need to keep front and center. The EU's GMP Annex 1 calls for appropriate pressure differentials and a solid contamination control strategy. It also demands scientific justification for airflow patterns and continuous monitoring of critical environments. Meanwhile, WHO and PIC-S GMP emphasize effective pressure cascades, environmental control verification, and thorough investigations of any excursions. In the U.S., the FDA's CGMP focuses on preventing contamination and cross-contamination with proper environmental controls. These standards guide everything we do. Let's talk about airflow direction in cleanroom environments. The idea is simple. Air moves from higher-grade areas to lower-grade ones, starting at grade B, then grade C, grade D, and finally the corridor. This pressure cascade prevents contaminants from moving into cleaner spaces. Each area maintains a specific positive pressure. For example, grade B is at plus 35 pascals, while the corridor is only plus 5. This controlled pressure difference keeps the environment sterile and safe. Let's talk about positive pressure, a simple but powerful way to protect products. The idea is to keep the air pressure inside a room higher than the surrounding areas. This means air flows outward, not in, which helps keep contaminants away. It's used in places like sterile manufacturing, aseptic filling, and injectable production. For example, in a grade B filling room, the pressure might be 35 pascals, while the adjacent grade C room is at 20. That 15 pascal difference keeps the air moving out, safeguarding sterile products. Let's talk about negative pressure for containment, a strategy where the air pressure inside a room is kept lower than the surrounding spaces. This means air naturally flows inward, stopping any hazardous materials from escaping. It's commonly used with cytotoxic and hormonal products, high-potency APIs, and biological containment areas. For example, if a containment room is at minus 15 pascals and the adjacent corridor is at 0, air moves into the room. The big win here is protecting both people and the environment around us. When a facility makes multiple products, keeping them separate is a real challenge. Cross-contamination risks go up, especially with sensitive items like antibiotics, hormones, oncology drugs, or potent APIs. To tackle this, we rely on pressure-based controls. That means dedicated pressure zones, airlocks, careful material transfers, and HVAC segregation. For example, an antibiotic suite might be kept under its own pressure regime to stop airborne particles from drifting into other production areas. It's all about creating barriers that keep products safe and pure. Let's break down how we calculate the pressure differential. It's simply the higher pressure minus the lower pressure. In this example, that's 34 minus 21, which gives us 13 pascals. Our acceptance range is between 10 and 15 pascals, so with a result of 13, we pass. This means the airflow barrier is working properly, maintaining the right pressure difference between grade B and grade C areas. Let's talk about monitoring and alarm management, a crucial part of keeping systems running smoothly. Here, we're focused on pressure monitoring, with specific targets and limits to watch. When pressure drops below the action limit, alarms go off automatically. That triggers notifications to quality assurance, and investigations get underway right away. We use a mix of instruments, differential pressure transmitters, digital sensors, and magnehelic gauges, all feeding into platforms like BMS, SCADA, or environmental monitoring systems. This setup helps us catch issues early and respond fast. Let's look at a common failure scenario, when the pressure difference between grade C and grade D drops from 12 pascals to just 5. This might seem small, but it carries serious risks. Contamination can migrate, and environmental segregation breaks down. To manage this, we need to investigate the deviation, assess any product impact, and implement corrective actions. Causes often come from HVAC issues like fan or damper failures, operational problems such as doors left open, or instrument errors like sensor drift or calibration mistakes. When we get pressure differentials right, the benefits ripple through every part of our operation. First, product protection improves, contamination risks drop, and sterility becomes more reliable. For personnel, it means safer conditions, especially when handling hazardous materials. On the compliance side, we meet GMP standards more confidently and stay inspection ready. Operationally, stable environments reduce deviations, keeping things running smoothly. Achieving this relies on best practices, from scientifically designed pressure cascades and qualified HVAC systems to continuous monitoring, alarm management, and thorough investigations. It's about integrating all these elements into a cohesive system that maintains data integrity and drives excellence. Pressure differential management stands out as one of the most effective ways to prevent cross-contamination in pharmaceutical and healthcare manufacturing. By carefully controlling airflow from cleaner to less clean areas, we reduce the risk of contaminants moving between rooms or processes. When combined with strong HVAC systems, ongoing monitoring, and a solid contamination control strategy, pressure differentials act as a reliable barrier against microbes and particles. This approach not only safeguards product quality and patient safety, but also ensures compliance with key regulatory standards. It's a critical part of a smart, risk-based contamination control program. Thanks for joining me today. If you want to dive deeper or have any questions, please don't hesitate to reach out. I appreciate your time and attention, and I look forward to continuing the conversation. Thank you. This video was created with SlideSpeak. Visit SlideSpeak to turn your presentations into engaging AI-narrated videos.